Hello everyone. In our previous lecture, I gave you an overview of how kind of the history of the MODFLOW model and how it's organized into processes and packages. We talked about the required packages, and now we're going to look at some of the optional packages that are very commonly used, and they do have some common features or parameters associated with those, such as conductance, which we'll talk about. And there are a lot of optional packages, so I've decided to break this lecture up into two parts. We're going to talk about some of the more commonly used ones here, and then next time we'll look at some common ones and then some that are a little bit more specialized. And so here we go. Here is the list of optional packages that I showed in our last lecture. We are going to specifically look at the drain, recharge, and well packages in this lecture. So let's start out by looking at the well package. This is obviously one that is really commonly used. Wells are assigned to individual cells. So when you can define 1, 2, 3, 4, up to thousands of wells associated with your model, and each well is then assigned to an individual cell. So each instance of the well has an I, J, and K index indicating the well that it's located in. Now, we don't really designate where in this cell the well is located. It doesn't really matter. As long as it's anywhere in the cell, we just assign it to that cell. And then we also, it's really a simple package. So you tell it what, for each well, you tell it what cell it's in, and then you also assign a flow rate Q. And this Q can either be steady state or transient. Steady state means it's a single Q value that applies during the entire simulation, or transient means you can have it vary over time throughout the simulation, and you can have a separate value for each of your stress periods, as they're called. The Q value can either be negative or positive. And again, the sign, whenever we're talking about flows with MODFLOW, we use a consistent sign convention. A negative Q means water is going out of the aquifer. A positive Q means water is going into the aquifer. And so most of the wells we deal with in aquifers are extraction wells or with groundwater withdrawal wells, where we're pumping water out of the aquifer, and therefore these are always assigned a negative pumping rate. The pumping rate is in volume per time. So if your length unit in your model, as defined in the basic package, is meters, and if your time unit is days, you would enter it as cubic meters per days. And something that needs to be emphasized, whenever you prepare input for any of these packages, you have to put it in the proper units. The model doesn't do unit conversion for you. You have to prepare your data in the appropriate unit, and something you have to be careful with. But that's about it for the well package. It's really simple. Coming up with an appropriate pumping rate can be really challenging, especially for a large aquifer with a large number of wells. It's not common for pumping rates to be recorded over time, so you have to use estimates as to how much water's been pumped and when it was pumped, and that can be a pretty challenging part of your data preparation process before you begin to develop the model. Next package we want to talk about is the drain package. Again, these are assigned to individual cells. You identify an I, J, and K layer. These are typically used to simulate agricultural drains or springs or some other location in your model that's a little bit lower in elevation, where water can discharge from the aquifer to the ground surface. Now this is a one-way feature. A drain is always a sink, meaning it can only pull water out of the aquifer. It cannot put water into the aquifer. So if the water table in a cell is above the elevation of the drain, water will leave through the drain, but if the water table is below the drain, there's no impact. We'll show this in the subsequent slides. And so there are two, in addition to the cell where this is assigned, there are two required parameters, the elevation of the drain and something that is called the conductance. And we'll talk about in a second how to define the conductance. So here's a graphical example. This would be an example of an agricultural drain. You have a pipe in the ground and it's surrounded by some material. Maybe this is backfill. I don't know, some kind of material that is a different material than the aquifer. The aquifer is in the background, and this blue line represents the water table. And so the head at this location, so this drain is assigned to a specific cell identified by a row, column, and layer. So that's why we write H-I-J-K. That's the head of the particular cell. I is the row, J is the column, and K is the layer. It's a common notation we use to indicate the head of the cell. And then this bottom of the drain is the drain elevation. And inside the code, it's the variable used for that is delv, but it's the drain elevation. It's one of the things you have to input. And another thing you have to input is the conductance, which we'll designate here as CD. The conductance represents both the geometry and the hydraulic conductivity of these materials surrounding the drain. The idea being, as the water goes from the aquifer to the drain, it has to pass through these materials, and that could result in a small head loss depending on the relative conductivity of the drain materials versus the aquifer, and also the geometry of these materials. And we'll talk more about that in a second, how you go about deciding what to use for the conductance. And so when the head is above the drain elevation, as shown in this diagram, the flow rate from the aquifer to the drain is the conductance times the head difference between the head and the cell. And actually, to do the head difference, we used the drain elevation minus the head. Now, if you look at the diagram here, the drain elevation is below the head, so the drain elevation minus the head is going to be a negative number, a negative head difference. But that's good, because the resulting flow rate should be negative because it represents water leaving the aquifer into the drain. And so that is the proper sign. And so that flow rate is equal to the conductance times the head difference. Now, if the drain is below, if the head in the cell is below the drain elevation, then the flow rate is simply 0. So if you think about it, if the let's back up a little bit. So when the head is above the drain, the flow rate is the conductance times the head difference, and the greater the head difference, the greater the flow rate. So it can vary linearly, and as if you imagine that head at the cell gradually dropping, the closer it gets to the drain elevation, the smaller this head difference gets, and the smaller the discharge, the lower the discharge is from the aquifer to the drain, until eventually, if the head drops below the drain elevation, then it's too low. There's no water to feed into it. So you can think of this, it'd be like a spring going dry. In fact, sometimes we use the drain package to simulate a spring, because the way a spring works, if you have a high water table, it discharges to the ground surface, and if you have a low water table, it can dry up. And so the drains are very useful, and there are other locations where you have just marshy areas. Sometimes we call them seeps, where the ground is saturated and water discharges to the surface. Well, that only happens if the water table is high. If the water table is low, there's no impact. And so sometimes we use drains just to represent an area in our model where if the water table gets high enough, it's just going to discharge. Now, you would think, why doesn't that always automatically happen? If the water table gets above the, let's say, the top elevation of your MODFLOW grid, no, that's not the case. It only happens if you tell it, if you mark that as a drain cell and give it, say, like a really high value of conductance or something. So drains are very useful and very commonly used. Now, one of the key parts of a drain is the conductance. What is the conductance and how do you calculate it? And to understand that, we have to go back to Darcy's law. Remember, it's Q is equal K times delta H over L times A, where Q is the flow rate, K is the hydraulic conductivity, delta H is the head difference, L is the length of flow, and A is the gross cross-sectional area of flow. It is possible to rewrite Darcy's law as Q is equal to C times delta H, where C is basically everything on the right-hand side except for delta H, Ka over L. Now, if you think about it, what the C term, which we call conductance, is the permeability, the hydraulic conductivity, the area of flow, and the length of flow. So this is basically the intrinsic, so the underlying hydraulic conductivity and the geometry of the problem. And so we can lump that into a single term, and then our flow rate is simply the conductance times the head difference. And so the appropriate values to use to calculate your conductance, the values of Ka and L, you just have to determine that on a case-by-case basis and based on your understanding of Darcy's law and what that means. So, for example, suppose that we have a river that crosses a cell. And by the way, in our next lecture, we're going to talk about the river package. The river package also uses conductance. So this is why this example has been built this way. And so this red zone right here would represent the portion of the river that overlaps a cell, and it has a specific length. And basically, the conductance for a river represents the river bottom sediments, and the water in the river is, whether it's coming from the aquifer to the river or going from the river to the aquifer, it flows vertically through these river bottom sediments between the river and the aquifer. And so to calculate the conductance, we take the hydraulic conductivity of the riverbed material and we multiply it by the cross-sectional area of flow. Well, in this case, since the water is flowing vertically, the cross-sectional area of flow is the length of the reach times the width of the reach. So this A becomes L times W. And then the length of flow is the vertical thickness of these riverbed materials, which we've designated as M. So for this particular case, the cell conductance would be calculated as KLW divided by M. Now, if you go back to our case here, if you can imagine this cross-section being extruded along the length of a pipe, for the length of the drain that overlaps a cell, you'd get a length, and then the width for the area of flow would be maybe the width of the bottom, and then the distance of flow, well, it's going to be, it could be flowing from here to here, or here to here, or here to here, but you know, some average of those distances. Now, The fortunate thing, whether you're using the conductance of a drain or a river, you don't have to stress too much about, do I have the right width of the sediments, or do I have the right thickness of the sediments? Because remember, you're also inputting a hydraulic conductivity, and I can guarantee you're not going to be able to calculate that hydraulic conductivity very accurately. So it's perfectly fine to make a guess at these values. And as we will discover as we use MODFLOW, the model is not terribly sensitive to conductance. I mean, it makes a difference. You have to put some thought into it, but it doesn't have a large impact on your model results, so you can get away with guessing and it works just fine. Okay, so this conductance term is used not just by the drain package, but by several other packages as well. But now we have an introduction, and we are going to, through the exercises and homework assignments, we're going to have a lot of opportunities to calculate conductance. And so it's something that should become second nature. Again, you just think back to Darcy's law, Ka over L, and it's pretty easy. It's a pretty simple thing to calculate. Now, finally, we want to talk about the recharge package. Recharge represents percolation into the groundwater from rainfall. And in this case, since it's coming down through the top of your grid, you assign one value to each vertical column. What I mean by a vertical column is for each ij value. So if you look down at the very top of your grid, it's like a two-dimensional array of rows and columns. For each of those cells, you input a value. Doesn't matter how many layers you have, and that's because the recharge is coming into your model vertically through the top. And of course, this represents the recharge due to precipitation. Again, it can be steady state or transient. You can do a single value, or you can have it vary with time. And you have to enter it in the correct units. The correct units are length per time. And so if your length unit is meters and your time unit is days, you have to convert it to meters per day. So for example, let's suppose that how do you come up with a recharge rate? A really common metric that we use is say 10 to 20% of recharge is a good rule of thumb to remember. Or excuse me, 10 to 20% of annual precipitation will often find its way down. It could be less than that, it could be more than that, but that's a good rule of thumb to start with. So let's suppose for a particular location that you get maybe a meter per year, 100 centimeters per year of rainfall. And so let's assume that 15% of that, so 15 centimeters, ends up being your annual recharge in that location. And that would be a relatively wet location. And so if your length units are meters, you would take 0.15 meters, and then to get it to meters per day, you would divide by 365. And that's a typical way of how you'd go about estimating, or excuse me, coming up with recharge in the proper units, and also estimating a rule of thumb. There are a number of things that impact recharge. So you get precipitation falls down. A lot of that precipitation is captured in what we call soil moisture, and it resides near the surface. Some of that evaporates. Some of it is lost through transpiration to plants. some of it runs off before it even has a chance to infiltrate. So regions that have a steeper slope sometimes have less recharge. And also the land use has a really significant impact. If you have inside a city, you generally get much less recharge because a lot of the surface is paved or covered with buildings. And so it's less likely to infiltrate. And then, if you have a fine-grained or clay material, it's more likely to run off or be captured before it percolates down. If you have a sand or gravel superficial materials, it's more likely to seep down and enter the recharge. And so all of those things can be considered as you come up with a recharge rate. I will say that, and we'll try to reiterate this over and over again, but the two parameters for a groundwater model that have the greatest impact are recharge and hydraulic conductivity. The solution is extremely sensitive to recharge. It represents the primary source of water to an aquifer. And so, the assumption you make can have a big impact, which is kind of scary because we don't really have very accurate ways of estimating recharge. The best we can do in a lot of cases is to do an estimate. I have seen people do surface water models, runoff models to estimate recharge, and that's fine. But in the end, we often end up adjusting the recharge as part of our calibration process, both the recharge and the hydraulic conductivity, until our model output matches the behavior we observe in the field, and then we can start to get some confidence that maybe we have a recharge rate that is pretty reasonable. So in a lot of cases, you'll just assume a constant recharge over your model domain. Sometimes you'll break up your model domain into different regions based on its slope and land use and vary the recharge. Other things can affect recharge if you're doing irrigation and applying a lot of water to agricultural land. That can lead to increased recharge. So those things need to be factored in as well. But again, it's a pretty simple and straightforward package. Just estimate your recharge, put it in the right units, and assign a value for each cell in the top layer of your grid typically, and then you can begin to use the recharge package. So that concludes each of the packages I wanted to talk about in this lecture, and we have enough information now to we can start building some models, and then we'll come back in a future lecture and talk about some additional optional packages.